Lake Mead is dying. The white bathtub ring scarring its canyon walls marks hundreds of feet of lost water. Decades of drought written in mineral deposits. Canyon walls stand exposed. Marinas sit on dry concrete. And somewhere beneath that shrinking surface, a tunnel punches through solid rock. 20 feet in diameter, 3 miles long, reaching deeper than any municipal intake ever built in North America. The third straw, a $1.5 billion tunnel built because the first two straws are already failing. One exposed to air, the other inches from the same fate. 2.3 million people depend on water pulled through this single system. The lake is dying, but the city cannot stop drinking. What happens when a desert metropolis bets everything on one tunnel that cannot fail? The answer involves 600 feet of water pressure, pumps that run around the clock, and a maintenance window of exactly 0. Las Vegas receives roughly 4 inches of rain per year. The Mojave doesn't negotiate. Summer pavement reaches 150 degrees. Evaporation steals water faster than the city can store it. But the valley kept growing, past 1 million. Then 2 million residents, in a desert that naturally supports almost none of them. 90% of southern Nevada's water comes from a single source. Lake Mead. One reservoir feeding a sprawling metro area. Golf courses, casinos, fountains, suburbs pushing into the sand. Here's the problem. That single source is vanishing. If it disappears, Las Vegas doesn't ration water. Las Vegas loses water. Entirely. Lake Mead peaked in 1983. Nearly full. Then came the Millennium Drought. The worst dry period in over 1,000 years of tree ring records. By 2010, water levels had dropped more than 100 feet. By 2022, another 50. The original intake pipes were built assuming the lake would stay high. Intake 1 sits at elevation 1,050 feet. Intake 2 at 1,000. When lake levels drop below those pipes, they don't slow down. They suck air. And a city without water doesn't have days to find a solution. Southern Nevada Water Authority faced a brutal calculation. Pray for rain, or build something unprecedented. A third intake, deeper than any before, drilled beneath the lake bed itself. Target depth, elevation 860 feet. Low enough to function even if Lake Mead dropped a dead pool, the level where Hoover Dam can no longer release water downstream. The engineering challenge was staggering. Drill 3 miles through rock under an active reservoir. Without flooding the tunnel. Without collapsing the lake bed. Without killing everyone inside. The price tag, $1.5 billion. The largest infrastructure investment in Nevada history. And there was no backup plan. Getting water from the lake was never the miracle. Getting it from 600 feet down continuously, forever, without interruption, that was the problem no one had solved at this scale. Camera pushes into darkness. A tunnel boring machine. 440 tons of rotating steel. Grinding forward at walking pace. Cutter heads chew through sandstone, siltstone, volcanic rock. 23 feet of diameter. Each rotation carves another inch toward the lake. Behind the cutting face, crews work in shifts, lining the tunnel with precast concrete segments. Hydraulic arms press each curved section into place. Grout fills the gaps. The tunnel grows behind the machine like a concrete snake swallowing distance. Typical progress, 40 to 60 feet per day. 3 miles total, roughly 18 months underground. And above them, a lake. Workers operate under pressurized conditions typically reserved for deep-sea saturation divers. Not underground. Airlocks. Hyperbaric chambers. Decompression cycles lasting hours after each shift. The grinding vibration of the TBM reverberating through pressurized air thick enough to taste. Down here, a fire or equipment failure doesn't mean evacuation. It means waiting. No fast escape exists. The only way out is the same slow shaft they came down. The tunnel runs 600 feet below the lake surface at its deepest point. That translates to approximately 260 pounds per square inch of hydrostatic pressure. Enough to crush unprotected structures instantly. Every concrete segment engineered to resist that force. Every bolt torqued to specification. Every grout seal inspected before the machine advances another foot. One weak segment. One missed defect. And Lake Mead doesn't seep through. It explodes through. But the machine keeps turning. The finale? Breakthrough. The boring machine grinds through the final feet of rock beneath the lake bed. But the lake can't flood in yet. Engineers install a massive concrete plug at the tunnel's end, sealing it until the entire system is ready. Meanwhile, divers descend through murky green water, near zero visibility. They guide a 700-ton concrete intake structure onto the lake bed itself, fitted with screens to filter debris, positioned hundreds of feet below the original lake surface. The deepest municipal intake of its kind in the United States. The intake sits below, invisible from shore, waiting to pull water through 3 miles of tunnel, over $1 billion buried. Now it has to work. Gates open. Pressure equalizes. Water rushes into the tunnel for the first time. The low roar of flow. Vibration transmitted through concrete. Systems performing as designed. Water doesn't climb on its own. The intake sits at elevation 860. The treatment plant sits higher. Gravity delivers water from the intake to the pumping station. But gravity alone isn't enough. The pumps are the non-negotiable lifeline, responsible for lifting every gallon hundreds of feet uphill to the treatment plant. Without continuous power, without continuous maintenance, without continuous vigilance, the tunnel is just a very expensive hole in the rock. Inside the low lake level pumping station, the floor vibrates. Pumps the size of buses humming at frequencies felt in the chest. Electric motors spin massive impellers. Water surges upward through pipes 8 feet in diameter. These pumps are engineered for continuous duty. Oversized bearings to absorb lateral stress. Impellers balanced to minimize cavitation. Housings mounted on isolation pads to dampen the vibration that would otherwise fatigue surrounding concrete. Construction costs for this station alone, over $650 million. It runs around the clock, every day. Because the city above never stops drinking. Every pump requires continuous electricity. A power failure doesn't mean reduced flow. It means zero flow. Within seconds. Redundancy is built in. Failure is not an option. Raw lake water isn't drinking water. It carries sediment, organic compounds, trace contaminants from a watershed spanning 7 states. But water drawn from 600 feet isn't the same as surface water. Temperature drops. Dissolved oxygen plummets. Mineral concentrations, iron, manganese, hydrogen sulfide, increase in layers undisturbed for years. At the treatment plant, technicians hold sample jars to the light. A faint greenish tint. The sulfuric smell of lake bottom chemistry. Coagulants bind suspended particles. Settling basins let gravity pull the clumps down. Filters catch what remains. Ozone attacks microorganisms. Chlorine finishes the job. As lake levels continue dropping, the intake draws from increasingly stagnant layers. Water quality becomes a moving target. The deeper the city drinks, the harder the treatment plant works. Clean water is achievable, but the energy cost of this depth is permanent. Follow the transmission lines from the pumping station across empty desert. Toward distant power plants, redundant feeds enter from separate grid sectors, engineered so a single line failure cannot cascade. Backup generators stand ready, sized for critical pumping loads. The electrical hum of transformers radiates heat into the desert air. Every gallon lifted costs energy. Every treatment chemical costs money. Every inspection, every repair, every equipment replacement adds to a bill that never stops. The annual figure measured in tens of millions of dollars. And this isn't temporary. Unlike shallow intakes where gravity assists, intake no. 3 fights gravity from the lowest possible point. Every gallon must be lifted hundreds of feet. The energy demand isn't operational overhead. It's structural, permanent, baked into every gallon. They solved the depth problem. They traded it for a power dependency that never ends. Night shift at the control room. Screens glow with real-time maps. Every pump, every valve, every reservoir, every pressure reading across the system. Operators watch flow rates like pilots watch altitude. Pumps wear out. Intake screens collect debris. Concrete ages under pressure. Divers descend periodically to inspect the intake structure in near-zero visibility, checking for damage, clearing obstructions. Tunnel inspections require specialized equipment and crews willing to work miles from daylight. Every component has a projected lifespan. Every lifespan requires budget allocation years in advance. One deferred repair becomes a vulnerability. One vulnerability becomes a failure point. This isn't a project with a completion date. It's permanent infrastructure triage. The third intake isn't a monument you build once and forget. It survives on maintenance schedules that can never be cut. Not a marvel to admire. Life support. Return to Lake Mead. The bathtub ring isn't a scar. It's a countdown. Dead pool. The elevation below which water no longer flows downstream to other states. And Hoover Dam stops generating power, stops releasing water entirely, triggering legal and political chaos across 7 states that depend on the same river, a threshold that once seemed theoretical. Intake No. 3 is designed to function nearly to dead pool, the city's final margin, hundreds of feet deeper than the straws that failed before it. The engineering works. The hydrology might not cooperate. Even the third straw has a floor. And the lake is still falling. Las Vegas sprawls across the valley. Impossible. Improbable. Entirely dependent on a dying lake and the tunnel reaching beneath it. Fresh water flows through taps across the valley. Clean, safe, uninterrupted. But now you know what runs beneath. 3 miles of tunnel, pumps that never rest, and a lake that keeps falling. Not an intake. A feeding tube, not a tunnel. Life support. The machine can never stop.